Hi, and welcome back to another episode of Discrete Mathematics. In the last lecture, we learned that interpretations associate symbolic expressions with corresponding meanings in some domain of discourse. You've already learned how this works, from first grade on. In basic arithmetic, for example, we use numerals to represent numbers. A numeral is an expression that we might write down on paper. So, for example, the numeral 6 represents the number 6. When we look at a 6 on a paper and see that numeral, that symbol written down on the paper, our minds just jump immediately to the concept of, sixness, you might call it. But the symbol is just a symbol. It's an expression. And the concept that it means is a mathematical abstraction. In this case, the natural number 6 or the integer 6, as the case may be. So we can say that, when you write down the numeral 6, that you've written down a literal expression. And it's a literal expression in the sense that the expression literally means the number that it represents. We could just say, the expression 6 means the natural number 6. And I want you to start to distinguish those two concepts, expressions from their meanings. They're tied so closely together in our minds that we generally kind of conflate symbols and meanings, and that's a very useful thing to do because then we can reason in our minds symbolically, and the mathematics behind those symbols is almost completely transparent. But really, numerals are different than numbers. And again, another way to see this is that many different numerals can be used to represent the number 6. So for example, we can use the standard, decimal digit 6 to represent the natural number 6, or we could use the binary expression 110 to represent the number 6. Why does 110 represent 6? Well, it's 0 times 2 to the 0, which is 0 times 1, which is 0, plus 1 times 2 to the first power, so that's 2, plus 2 times 2 to the second power, which is 4. So 110 means 4 plus 2 plus 0, 6. Okay, so different numerals can represent the same concept. So we really do have to separate the concept of, or the ideas of expressions, numerals in the case of expressions that are literal expressions representing numbers, from the concept of, the numbers that they actually represent. So once again, we have a syntactic domain of symbols, and we have a corresponding semantic domain of the meanings of those symbols. In this case, we're going to use decimal numerals to represent as literal expressions for natural numbers in the semantic domain of arithmetic. Okay, now the same principles hold for more complex expressions. So in algebra, for example, in 8th or 9th grade, you learned that we can use variables or identifiers like n to represent mathematical meanings. So at some point in a mathematical presentation, somebody would have said, let n represent the number 6, for example. And then later on, they'll use the expression n instead, and we could call that an identifier expression. They'll use the identifier expression n instead of the literal expression 6 to represent a mathematical concept. And what does n mean? What does the expression n mean? Well, it means whatever the expression that it's bound to means, right? So if n is bound to the literal expression 6, then n means whatever the literal expression 6 means. And the literal expression 6 means the natural number 6. So the identifier expression n in that context or in that environment in which n has been bound to the literal expression 6, and the meaning, the semantics of n, what it means in the domain of arithmetic is the natural number 6. An even more complex example is the expression, say, 6 plus 5. Okay, so how do we think about that as a syntactic thing? Well, the 6 and the 5 are both literal expressions, And then the plus is a kind of a way of gluing those two expressions together into a larger expression. And we'll call that a function application expression, or just an application expression, because it represents the application of some function, in this case addition, to some arguments. In this case, whatever the literal expressions 6 and 5 mean respectively. Here they obviously mean the natural number 6 and the natural number 5. And the symbol plus actually means in the arithmetic domain, the function addition. Okay, so if we want to now ask what's the meaning of that expression 6 plus 5, well, we say it means whatever it means, the application of the corresponding real mathematical addition function to the values of those literal expressions 6 and 5. And, again, in our minds, this may sound very pedantic, and in a way it is, but in a very fundamental way it's not, because we're talking about languages, like the language of arithmetic expressions, their syntax, versus semantics, what they mean. And this concept is absolutely central to all of computer science. Programs are just expressions in some language, and we need to understand not only the syntax of those expressions, but what they mean, what they compute. So this notion of languages, of expressions, with rules for telling you what those expressions actually mean in whatever domain they are associated with, is really very central to all of computer science. Okay, so in Lean, in Java, in Python, in C++, you name it, what an arithmetic expression means, an arithmetic expression being a string of symbols, an arithmetic expression being symbolic, what it means, that piece of syntax, what it means, what its semantics are, some natural number. Okay, so if we took the expression, again, 6 plus 5, viewed as a syntactic object, a string of symbols, then an interpretation associates that string of symbols with a meaning, which is the number, the natural number that expression evaluates to or reduces to when we evaluate that expression. Okay, so that's what we're going to talk about in today's lecture. Okay. In this lesson, in particular, you'll learn rules for evaluating these three kinds of expressions that we've just talked about. We've talked about literal expressions, identifier expressions, and application expressions. Literal expressions are expressions like 6 that just literally represent a corresponding value. Variable expressions use our variable names or identifiers like n or p or q or max velocity or whatever you want to call your identifiers. Okay? And what they mean is what the expressions that those variables are bound to mean. So if n is bound to the literal expression 6, then n means the natural number 6. If n is bound to the application expression 6 plus 5, well, then what n means is what that expression means. That expression means 11. So that expression evaluates or reduces to 11. So when we reduce or evaluate n, we first reduce it to that expression, 6 plus 5, and then we further reduce that expression by evaluating the application of the plus function to the values of the literal expressions, 6 and 5, to get the value 11. Okay, so again, what are those three kinds of expressions we're going to talk about? Recite them. Literal expressions, identifier expressions, application expressions. Learn that, okay? Learn what each of those kinds of expressions looks like. And you already know this stuff from programming. You've already been using these concepts all along. You understand how to write a literal expression in Python, x equals 7. Well, on the right-hand side of the equal sign is a literal expression. Okay, on the left-hand side is an identifier, and that assignment operation binds the value 7, albeit maybe only temporarily, to the identifier x. Okay? In Lean, it's even simpler. When you bind a value to an identifier, it can never change after that point. So there's no updating of identifier values in Lean. It's a pure functional language, which makes it much easier to reason about things in this language. Okay, so the nominal purpose of this lesson is to teach you basic syntax of expressions and how they're evaluated in Lean. And these ideas apply to evaluation expression across a very broad range of languages, including kind of at a high level, Java, Python, C++, and most of the other languages you've been looking at. There are differences, but the lessons basically apply. Okay. One of the characteristics of Lean is that every expression in Lean has a type. And the type of an expression is the type of the value to which that expression reduces. So if when we evaluate an expression that yields a natural number as a meaning, then we would say that the type of that expression is natural number. In Lean, the Lean libraries provide a type called Nat, which is the type whose terms represent natural numbers. So to represent arithmetic expressions in Lean, we have literal expressions that evaluate directly to natural numbers, variable expressions that evaluate to other expressions that eventually evaluate to natural numbers. We have function application expressions that evaluate to functions, that take some arguments, that evaluate to natural numbers, that then are combined by those functions to produce natural numbers. So we would say that the type of an expression, an operator, or an application expression in Lean, such as 6 plus 5, is also an expression of type Nat. Okay, so every expression, every term, and that is a piece of terminology that we'll use more and more frequently, every expression, every term in Lean has a type. And one of the primary characteristics of Lean is that it has what we call strong static type checking. Static means that type checking happens when you write the code, not when you evaluate it. Strong typing means that no type errors are permitted at all. So Lean will invariably tell you if there's a type error in your code. Compare that with Python, where you can write whatever you want and run it. And it's only when you actually run the code that you find out if you have a type error. Yeah, if you're sending a mission to Mars, you might want to know if you're going to get a type error when you try to enter the atmosphere. You might want to know if you have a type error in your code before you launch the rocket, so that when the ship tries to enter the atmosphere, you don't end up with a unexpected runtime type error saying, you're trying to add a number and a string here, and that doesn't make any sense. Okay. So, whereas the nominal purpose of this lesson is to learn basic Lean syntax and semantics, you're going to learn these concepts of syntax of a formal language and its semantics in a deeper way. And in particular, what you're going to see, and maybe you've seen it already, is that we can define the syntax of a language inductively. And then we can define a procedure for evaluating or reducing expressions in a language that's recursive. We build larger arithmetic expressions out of smaller ones, typically by applying function operations to smaller expressions. So if 6 is a literal expression, which is a kind of expression, and 5 is a literal expression, which is a kind of expression, then plus 6, 5 is also an expression, an application expression. And it's an expression, it's a bigger expression. And then we can say, well, 6 plus 5 in parentheses plus n. Okay, and that's a bigger expression. And then we can take that expression and use that expression as an argument to a times operator. And we take that big tree of operations and make it the right-hand argument of some other operation. Okay, and so we can see that we can build bigger and bigger expressions out of smaller and smaller ones with literal expressions and identifier expressions at the bottom or at the leaves of the tree. And then we'll see that we can write an evaluator that, well, we can think about evaluation as taking any expression. It could be a literal expression or an identifier expression or an operator expression with arbitrarily large sub-expressions as its arguments. We can define evaluation as a function that takes any expression, no matter how big, and kind of recursively evaluates the sub-expressions, if there are any, to get what they mean, and that then combines those meanings using the operation at the top of the tree. Okay, so it's really cool. This is fundamental to how we specify formal languages, like programming languages or a very simple language of arithmetic expressions, and how we associate meanings with every expression that can be built using the rules of expression combination. In this way, we end up with an interpretation for an infinite set of expressions. We can build infinitely large expressions, but with one small recursive procedure, we can evaluate the meaning, reduce any such expression to its meaning, which is just the natural number that it represents. Okay, in this lecture, we're going to use Lean's library-provided Nat Type, a type whose values are used to represent natural numbers in Lean, and we'll use operations that Lean has defined for us already, functions that it's already defined for operations like plus and times. Okay. So once you get through this preliminary material, you'll actually know a lot about the syntax and the semantics of Lean, because basically you're writing expressions within Lean, and the principles that apply to your very simple arithmetic expression language apply more generally throughout Lean in general. Okay. Now, we're not going to actually implement a language, the syntax and semantics of an arithmetic expression language in this particular lecture, but that will come very shortly using the concepts of inductive data type definitions and recursive functions that we've already begun to see and to practice implementing in this course. The rest of this presentation for today, we're going to answer a few questions and learn a few additional concepts. First, what is a Lean project? Second, how do I create one? Third, how do I edit one using VS Code? We're going to learn or see again that every term or expression in Lean has a type. We're going to learn again that Lean is a strongly and statically typed language. By strongly typed, we mean that no type errors ever go undetected. By statically typed, we mean that type errors are detected before expressions are evaluated or run. Okay? So essentially, the compiler, before a program is ever executed, is responsible for detecting type errors in the Lean code that we type. So welcome to a statically and strongly typed language. That's sort of like Java. As opposed to Python, which is dynamically typed, right? You don't get type errors until you actually run code that has a type error in it, and then you get a runtime exception or error message, or your code just malfunctions. We're going to see what literal identifier or variable expressions and function application expressions look like in Lean, and we'll see what it looks like to get a type error in Lean. Okay, so what I'd like you to do, if you would, is please crank up your, just follow along with me in this video. Maybe you want to put this window side by side with your Lean window on your laptop. It'll really help you to follow along. Okay, good. So let's get started with what we're up to here. A Lean project is a directory that contains a set of files and data files and subdirectories that are specifically set up to support editing of Lean projects. You shouldn't, from now on, ever create just a sort of a something.lean file sitting somewhere on your file system. You should create all of your Lean files within a properly configured Lean project directory. There's a tool for creating Lean project directories, and strangely enough, it's called Lean project. That's one word. It's a shell command, and I'll show you how to use it in just a minute. Okay. Once you've set up such a project, then you open that whole directory, not one of its subdirectories or data files, but you open the directory itself within VS Code. VS Code then looks at the files inside of that directory, and one of those files tells VS Code essentially what sort of project it is. So you should always open up the top level project directory in VS Code, never a parent of that directory, never a child of that directory. Open up the main project directory in VS Code. Okay, and then we'll just use VS Code as a standard kind of IDE to edit lean files within our lean projects. Okay, so let's have a look at what that looks like before we address any of the deeper questions. So here I am. I've just opened up this terminal window that you see, and I believe you can see my mouse pointer hovering around the shell's prompt here. Again, you can see on my machine, at least, having just opened this terminal window, my current working directory is set to the root directory of the simulated Unix file systems, well, to the root of that file system. And I really want to be working in my home directory. So on my machine, I'm just going to use the cd command with no arguments. The argument will default to my home directory. And now you can see with this tilde, the shorthand for my home directory, that I'm now looking at my home directory. If I use the pwd command, I can confirm that my current working directory is now /c, that's the C hard drive on my machine, /users, /sully, and I know that that's my home directory on this machine. Now, I want to create a new lean project for the work that we're going to be doing in this class. And I don't want to create it in my top level directory. I have a subdirectory on my machine called projects. It's a subdirectory of my home directory, and that's where I want to create my project file. I'd like you to stop the video at this point and think about where you want to put your top level lean project file for the work that you're going to be doing for maybe the next couple of weeks in this class. Students, in my experience, typically have, a subdirectory of their documents folder, for example, called, UVA work. By the way, best advice, don't put any spaces in your file names, and then subdirectories of that for the different classes that they take. So go ahead and figure out, what directory you want to set up to hold your CS2102 work this semester. Create that directory and then cd into it, and then we'll take it from there. Okay, so stop the video, go ahead and do that, and then restart the video and come on back. Okay, good. So here we are. I'm going to change into my preferred parent directory for my CS2102 subdirectory. So I am going to cd into my projects directory. I typed PRO and then hit tab for file completion. Okay. So I've changed into my projects directory. I'm going to see if I have a directory, ls-l to get a long listing, and D to get a listing of a directory file rather than its contents if I already have a CS2102 file. I have no such file here, so I'm going to make a CS2102 directory. And let's call it CS2102. By the way, you saw me use my arrow keys to move around on the command line, and that's something you can do if you forgot to type something earlier on the command line, or you type something wrong. You can see that you can move around on a command line before you execute a command in your bash shell. So there's my CS2102 file. I'm going to change into that directory. Okay, and now I'm to the point where I want to create a new lean project. And I need a good name for this file. How about my work? Okay, I want to create a new lean project called my work, again, within the CS2102 directory. So again, I can try pwd. That tells me I'm working within the Sully project CS2102 directory, and I want to create a new lean project called my work. The command to create a new lean project is, as I said, leanproject, all typed out as one word. So the first thing that I want you to do is check to see if you have leanproject installed on your system. If you did all of the setup properly, you should, unless I fail to give you some instructions. But let's see what to do here. I can see if leanproject is installed. by typing leanproject -- or -- version. And I have it installed on my machine, so it comes back and tells me, what version of the leanproject command is installed on my machine. And that's what you want to see. If you didn't see, if you got a command not found sort of error indicating that program is not installed on your machine, then you need to execute the following command. And I'm cutting and pasting this from my notes. You need to run and install the command pip3 --install --mathlib_tools. Okay, now I actually ran that command, and I got a bunch of warnings that say essentially that the software is already installed on my machine. Okay, good. So let me move on to the next stage then. We want to use the leanproject command to create a new project, again called my work. So let me clear my screen of this distracting information using the terminal's clear command. And now I can create the project file, leanproject. New is the first argument to leanproject, and it tells leanproject I want to create a new project. Leanproject has other functionality that can be invoked using different keywords. And I want, as a second argument, to give the name of the directory in which the project will be set up. So I will call that my work. Okay, I just hit enter to execute this command, and it's going to take a couple of seconds for this command to fully execute. What's happening here is that this leanproject command is downloading a bunch of files from a repository called GitHub and from some other places to set up your project. But now the command has finished. And at this point, if I do an ls in this directory, I see that my work is now set up. Okay. If I wanted to see what files are in there, I could, do a listing like this. And I see that there are 2 directory files, _target and src or source, and 2 data files, leanpackage.path and leanpackage.toml. And those are the files that leanpackage set up for us so that this is a properly configured lean project directory. We don't really need to worry too much about the details of those files right at the moment. So let's continue without going down the rat hole of seeing exactly what are in those files. Just trust me, you need them for everything to work. So make sure you've properly set up a lean project at this point. If you haven't been able to, ask me for help. Okay, and I'll give you help to make sure that that you're not left behind at this point in the class. Good. Okay, so our next task is to start to edit our new and currently quote unquote empty lean project. So I'm going to run the VS Code command from the command line. Sorry, it's not VS Code, it's code. And the file that I want to open is my work. Okay, so I can either open my work by typing code my work, or I could cd into the my work directory like this and say code dot, because dot expands to the current working directory, which is now the my work directory, as you can see right here. So these would be equivalent ways of opening up this lean project. Okay, so this is now the screen that you should see, the window that you should see on your screen. This is VS Code. And in the main part of the window here, we have a kind of a file open that contains a lot of welcome information. Welcome to VS Code. It includes some common commands that you might want to execute to open a new file, to open a folder or a project, and to do some other stuff. These are recent projects that I've had open in my VS Code environment. You won't have that list because obviously you haven't been editing the same projects I have. You have some helpful information over here, and we can kind of ignore all of this by closing out this little window here and being done with it. On the background screen here, you see a few shortcut commands. You know, if you want to show all commands, Control-Shift-P on my Control-Shift-P on my machine. You use that functionality previously to set your default shell in VS Code. We can ignore this stuff now too. Over here almost on the left-hand side of the screen, you have a bunch of tabs, one of which is a browser for the directory that you just opened. So here are the two subdirectories, _target and source. Here are the two data files that you saw, leanpackage.path and leanpackage.toml. And here's one file that you didn't see when we did an ls earlier. It's called begins with a period, git ignore. And there's a detail here you need to know. When you start a file name in Unix with a dot, that dot means that the file is quote-unquote hidden, which means when you do a standard ls or ls-l, that file won't be listed. If you want to see all of the files in a directory, you need to use the -a for all option. So ls-a will actually list all of the files, including the quote-unquote hidden files whose names begin with dot. So if you want to take just a second, you can stop the video at this point and bring up your terminal window and try an ls-a command, or you can combine options and say something like ls-la or that's a command I use very often, ls-la. VS Code by default shows you the hidden files in your project directory. Okay, down the leftmost column here, we have a couple of different tools. Your set of tools will vary depending on what additional software and what additional plugins or extensions you've added into VS Code. The topmost one is your project browser. You can open and close that window by hitting this option here. Command or Control B will also open and close that project browser. I ought to use the shortcut keys in general. Control B on my machine, Command B on a Mac. Okay, and you often want to close that to get some additional screen space for editing. There are some additional tabs going down here. You've also used the extensions tab here to add the leanprover extension to your VS Code environment. Those are two tabs that you're familiar with at this point, and I'm not going to talk about any of the other ones right now. Okay, good. Okay, so the next idea is that we want to start to create some lean files. Okay, and we're going to create all of our lean files within this currently empty directory called src, which we usually pronounce source. And to set up a source subdirectory of a project is very common practice across, Java projects, JavaScript projects, Python projects, and so on and so forth. You often have a directory to hold the source code for your project, and that's all that this is here. I can right-click here and say New File. And the nice thing about creating a new file this way is you can immediately give it a useful name. And please follow along with me. Have your VS Code environment running. And along with me, let's create a file called, let's call it Basic Expressions. Actually, you know what? I want to not do that. I'd like to create a subdirectory of source. First, let's call it Scratch. Okay, and this will be a subdirectory of the source directory that we can use just to sort of, it's like a scratch sheet, scratch paper for just kind of going through stuff that we don't intend to, for example, to submit as homework. Okay, let's create another directory of source. So I'm hovering over source, and let's create another subfolder. And let's call this, well, let's not do that. Let's just have our source folder and our Scratch subdirectory. Okay, I'm going to click on the Scratch subdirectory. So I'm now working there, and I'm going to right click and I'm going to create a new file within my Scratch directory. And that's going to be called basicexpressions.lean. Okay, now it's really important to understand that VS Code, the way that VS Code knows to activate the lean extension is that it's working on a file called something.lean. If you're working on a file called something.text, then the lean prover extension won't be active. So let's see that in action. Let's create a new file here called deleteme.txt. Okay. I can type all kinds of stuff in this file that makes no sense from a kind of lean perspective. I don't get any errors because the lean extension, which I can tell is running here by this stuff at the bottom of the screen, doesn't treat this as a lean file, so the extension's not going to do anything with a file like this. Okay, so I'm going to close that window. I don't want to save that file or the contents of that file. I'm going to come over here. I'm going to right-click on deleteme.txt and just delete that file from my project. Okay, so here we are. You can click on it again if you want to, working in the basic expressions.lean file. Okay, and this is where the real content of the rest of the presentation here begins. Okay, up until this point, I've showed you how to set up a new lean project, how to open it up in VS Code, how to create and remove files, including directories and subdirectories. And so now we're really ready to get going. So the rest of this presentation is really organized around the three kinds of expressions that we're going to, that we've talked about so far in lean. And these are literal expressions, variable or identifier expressions, and application or function application expressions in which a function is applied to some argument to represent the value that results when that function application is reduced or evaluated, or you can think of it as when you run that code. Okay, so let's start with an overarching concept that's really important in Lean, and this is true of many other languages as well, including Java. Lean is statically and strongly typed, as I said. And what that means is, among other things, that every expression and every value in Lean has a type. And you can ask Lean to tell you the type of any expression in Lean using Lean's hash or #check command. So the idea then is we can type pound, and I'll just call it pound, check, and then any term here, okay, any expression, and Lean will tell you the type of that expression. Now, all of the expressions that I'm going to use for this particular lesson are going to be of type Nat. The Nat type is defined in Lean's libraries and provides us a way to represent natural numbers in unary, in exactly the way that we've talked about extensively already. Okay, but I don't actually have to type out those values in unary. Rather, Lean understands that when I use standard numerals like 5, that it should assume that those numerals represent natural numbers. Okay, so you'll see here, as soon as I completed the check command by adding 5, over here on the right-hand side in the Lean info view, I get messages from Lean, and the first message tells me the answer to this command, that 5 is of type Nat. In other words, 5 is under the hood. Under the hood, it's a unary representation of a natural number. Okay, so 5 is of type Nat. And of course, if we check another expression like, I don't know, let's do another one. If we check 6, we find out that 6 is also of type Nat. Okay. Now, so 5 and 6 here, it's important to see, are literal expressions. Okay. Literal expressions. That expression 5 represents a natural number. So how do we get the natural number that the literal expression 5 represents? Well, for that in Lean, we can use a command called eval. So if we evaluate the literal expression 5, okay, we get the value 5. Now, I want you to go back and remember what we talked about before. Even though this 5 and this 5 look the same, you have to think of them differently. This is an expression in the language of Lean. This represents a natural number value. Okay, so here's an expression. This is syntax. Here's what it means when this expression is interpreted. Okay, under the interpretation defined for Lean, this literal expression evaluates to the natural number represented by this digit here. I mean, we have to have a way to see what number is being is produced by evaluating this expression. So these 5s look the same, but they're actually different kinds of things. One's an expression, and one just represents a value directly. Okay. So let's go ahead and evaluate 6, another literal expression, and there's the result of doing that. Okay. If you want to see the answers to all of these commands at once, you can open up this little tab here, and Lean will tell you give you the outputs for all of the commands rather than the one where the cursor is. So here I can click through these lines, and you see the output updating over here. So under the messages tab, you get one message at a time. Under the all messages tab, you can see all messages produced by these sorts of commands in Lean. Once you have more than 5 or 10 outputs, this tab here can get a little bit cluttered, and so it's often useful to close it down and just get one output at a time. Okay, so there's the notion of literal expressions. A literal expression here is a numeral that we interpret as representing some value. If we want to know the type of that expression or the type of that term, we can use check. And here the output tells us that term 5 is of type Nat. What does it mean that that term is of type Nat? Well, what it really means is that if I evaluate that term fully, if I evaluate that term, I'll get a value of type Nat. Okay, one of these unary representations of the number 5. Okay, so check tells us the type of a term. Eval tells us the value to which that term reduces. Okay, so I'm going to just use a little comment here. In Lean -- is the prefix on a line for a one-line comment, and I'll just label this as literal expressions. Okay, so again, make sure that you're typing along with me, and stop the video at this point if you want to take a minute to think about what we've just said. Okay. Next up is the notion of identifier or variable expressions. I don't care which of those terms you use. Variable expression is fine. Now, when you're using a functional language like Lean or OCaml or Haskell or another functional language, these languages have a property of variables that they are what we call immutable. So once you bind a value to a variable, you can't update that variable. So in a funny way, variable is sort of a strange name for an identifier whose value can never vary. In Python, you can say x gets the value 6, x equals 6. Then in the next line, you can say x gets the value 7. And if you now print out the value of x, y, it's 7. Okay, but in Lean, you just can't do that. And in other pure functional programming languages or other functional programming languages like Haskell and OCaml, you just can't do that. These languages are languages of functions and values and terms that represent them, and you can apply functions to values, but you can never update the values of variables. It seems very strange at first that you could even program in a language in which you can assign a value to a variable but then not update it. So really the way to think about variables in in these languages is not as identifiers whose values vary, but rather as identifiers that kind of generalize from a specific value like 5 to some arbitrary value. Okay, and the idea then is if you then write additional code in terms of those variables rather than in terms of the literal values they represent, then you have a kind of generalized piece of code rather than one that works only for a specific value. You'd have to go back earlier in your code and change the value to which a variable is bound, but then the succeeding code should still work fine. Okay, so the next kind of expression we're going to see are, okay, let's just call them variable expressions. Okay, or you can call them identifier expressions as I have up until now. So here is the way that you bind an identifier, a name, a variable name, to a value in lean. You define, so the keyword is def, a variable name, let's use n1, because we're going to bind this identifier or variable name to a value of type nat, okay? And here we can just say colon equals 5, okay? Let's make it 6. We can, what happens if we try to bind a new value to n1? Let's see, def n1 colon equals 7. Oh, we get an error. Invalid definition. A declaration named n1 has already been declared. Okay, and then some additional kind of error message that's a little bit impenetrable. But this is telling us that we're trying to assign a new value to a variable to which a value has already been assigned. And as I said, in a functional programming language, this is just not permitted. So on the other hand, if we pick a different identifier name, it'll work just fine. So let's let n2 be our value 5. Okay. Good. So now the question is, okay, what's the type? We've seen that the type of 6 is nat. So this is a literal expression whose value is nat, whose type is nat, because if we evaluate this literal expression, we get a nat. So the type of this expression is the type of the value to which it evaluates, which is nat. So the type of the expression 6 is nat. If we evaluate the expression 6, then we get the value 6. So how do those concepts play out here for these two simple examples? Well, let's first think about what we're going to get if we check the value of n1, check the type of the value of n1. Well, think about it this way. If we evaluate the variable expression n1, what do we now expect it to evaluate to? Well, we expect it to evaluate to whatever this expression evaluates. This expression is a literal expression 6, and it evaluates to a natural number, nat, a value of type nat. So n1 reduces to the literal expression 6, and the literal expression 6 reduces to or evaluates to the number 6. So n1 reduces to or evaluates to the natural number 6, which is of type nat, and so we would expect the type of n1 to be nat. And sure enough, when we check the value of n1, that expression, that variable expression, n1, is also of type nat, because nat is the type of value to which it reduces. If we evaluate n1, we expect to get 6. Okay, and indeed, that's exactly what we get. So check tells us the type of a term. Eval, and sometimes we'll also use reduce. Eval and reduce, I don't want to go into the difference between them. They both they use different evaluators to evaluate terms, and sometimes you need to use one, sometimes another. We'll see that later on. Not something to worry about right now. Just think of them as essentially doing the same thing, but reporting their results potentially in different ways. So if we evaluate or reduce the expression n1, it reduces to what the value it's bound to reduces to. So n1 reduces to what 6 reduces to, and the literal expression 6 reduces to the number 6, as we've seen here. So n1 reduces to 6 ultimately, and that's of type nat. So the type of n1 is nat, and of course the value of n1, the value to which that expression reduces, is 6. Okay. So I want to take a minute and talk a little bit more about types before we get on to the next topic of function application expressions. Okay, so that's what's coming next. But before I go there, let's talk a little bit about type checking. I want to give you a more elaborate version of these two commands. And so I'm going to copy those commands down here. And of course, I have errors on both of these lines. Question for you, why? Right, because I'm trying to bind values to these variables. Again, I'm not even allowed to bind the same value to these variables or any other value. I just need to change the names of these variables in order for these lines of code to work. So I'm just going to add tick marks or prime marks, they're single quotes, to these names just to make the variable names different. The tick mark or prime mark here has no mathematical significance. It just is a different a name for these variables. Okay, and now what I want to say is that like a slightly more elaborate version of the definition, in addition to defining the name of n1, also makes its type explicit. So the type of n1 prime here, we know is going to be nat. Okay, and so here's the kind of full-out version of, or almost full-out version of this kind of variable binding declaration or definition. Okay, we define n1 prime to be a term of type nat bound to the term 6, the literal term 6. And similarly, we can bind n2, a term that we declare to be of type nat, to 5. Good. Okay. So again, what are the elements of this expression? A keyword, def for define, a variable name that hasn't been used before, colon, the type of term to which we insist that variable name will be bound, colon equals, and then a term of this type as specified. So the term to which we bind n1 here better be of type nat. And indeed, this literal expression is of type nat. Now, if I try to bind n1, having declared n1, or n1 prime here rather, to be of type nat, if I try to bind that to a value of a different type, such as a string, then lean, without evaluating anything, without running anything, is going to tell me I have a type error. And so let's hover over this red underline, the squiggly red underline, and I get a type error message, type mismatch. The term hi has type string, but because of the declaration colon nat on the left, is expected to have type nat. Okay, and so lean simply will not let you get away with any type errors at all. None. You can't make a type error in lean because the type checker will catch you. Now, if you're used to programming in Python and not finding out if you have a type error until you run your code, and then having to trace through your code to figure out where your darn type error is, you will appreciate very much that lean tells you right up front whether or not there's a type error in your code. Okay, So, oh, my phone is ringing. Pardon me for just a minute while I hang up the call. Oh, spam call, they hung up on me. Let me turn my phone down so that doesn't happen again. Good. Okay. It's one of those video production things. It's like, you know, in Raiders of the Lost Ark, I think somebody was, you know, or never mind. Bad movie failures. This is a bad movie failure. Okay, onward. Good. So let's restore the correctness to this code. And so you see what we've got here. The last thing I want to tell you is that you don't need to use the expression NAT, the type name NAT. The lean environment, the VS Code environment here, and the lean language definition tell you can use \nat, hit a space, and then VS Code will substitute in this nice Blackboard script capital N, which is the symbol that mathematicians use to represent the set of natural numbers. Okay, and so the idea here is, you know, we're going to bind n2 prime to be a value of type natural number. And this sort of glosses over that distinction now between the unary representation of natural numbers that we're actually using here and the actual natural number that it represents. Remember, in our minds, we often kind of go back and forth very fluidly between numerals and numbers, for example. When we see 1, 2, 3, we don't think, oh, that's a numeral 1, 2, 3, and it's interpreted as meaning the number 123. We just look at it and immediately think of the number 123. So that's essentially what Lean is encouraging you to do here, to see through the intended interpretation of 5 here as a representation of the actual natural number that we call 5. Good. Okay, so there are many special characters that are available in Lean, and \nat is one of them. Again, the way you type that is \nat, then hit a space, and I typically then immediately hit a backspace, and hitting the space after that / special character string tells the programming environment to make that substitution. Okay, and now you'll understand when we go back to these check commands that they're telling you 5 is of type nat, but Lean uses the special character here instead of the string nat. Okay, so that's all that's going on there. Lean actually supports all kinds of mathematical notation, and so writing Lean is really like writing mathematics. And it's one of the reasons that I use Lean in this class. It's got a very nice environment. And after a while, it will feel not like you're programming, but that you're writing mathematics, that you're writing discrete math. Okay, so this is an environment in which you can read and write discrete mathematics using discrete math notation, just like the kind you'd find in books or mathematical treatises or published papers, or even in homework assignments in an algebra class. Okay, so let's now talk about arithmetic expressions, or application expressions. Let's eval the expression 6 plus 5. What do you think we're going to get? 11. Right. So let's look at this expression 6 plus 5 and think about how it's constructed. Really what we have here is a function symbol. So plus refers to some function, a function that takes two natural numbers as its arguments and that returns their sum. So we have a big expression here, a function application expression, in which the function plus is applied to two arguments, 6 and 5. In fact, in Lean, that plus that appears between the 6 and the 5 is really just sort of a shorthand for a function called nat.add. So this is the addition function for natural numbers applied to the arguments 6 and 5. So in lean, these two expressions mean the same thing. In fact, this expression just literally gets converted into this expression before this expression is evaluated. So because this expression gets elaborated is the word that we use in lean, into this expression, of course, these two expressions are then going to reduce to exactly the same value, which in this case is the 11 that we're seeing over here in the lean message window. Okay. So let's ask the next question. What's the type of this expression? Or of this expression here? And I'm going to put parentheses around this 6 and 5 so that we don't have any problems with grouping in a minute. What's the type of this expression? Well, how do we reason about that question? Well, we say that the type of an expression is the type of the value to which it reduces. And of course, we expect this expression to reduce to a value of type nat, namely 11, and we've already confirmed that it does. So because the type of an expression is the type of the value to which it will ultimately reduce, the type of this expression, so we'll use check and then copy and paste this expression to here, must be nat, and indeed the type of this expression is nat. So there are lots of similar expressions, so we could evaluate the expression 6 minus 5. This is another expression in which an operator, a function, takes two values of type nat and returns their result. Now let's talk in a little bit more depth about expressions versus their values. Here we have a big expression, 6 minus 5, built up out of smaller expressions. And let's actually write this as nat.sub 6, 5. Okay, that's the subtraction function. So this function application expression gets converted to this one, where all we're really doing is moving the operator nat.sub, the subtract operator, to come before its arguments rather than between its arguments. So these two expressions are exactly identical in meaning. This one uses something we call infix notation, where operators are placed between their arguments. This expression uses something called prefix notation, where operators are placed before their operands or their arguments. Okay? So let's think about this expression here. This is an expression in which a function is applied to some arguments. So this whole thing is an expression. But interestingly, it's an expression that's built up out of smaller expressions. So here we have a name, nat.sub. Just think of that as the name of the natural number subtraction function. Here we have a literal expression 5. And here we, 6 rather, and here we have a literal expression 5. So I'm going to give you a slightly simplified explanation for how this works. It's a little tiny bit incorrect, but we'll come back later and correct it. So we see that the syntax here is function name followed by argument expressions. Okay, and the fact that these can be expressions, well, we could have the first expression be 6 plus 5, and the next expression be 4, for example. Okay, so nat.sub is applied to two arguments, and each argument is an expression, an arithmetic expression. Here we have another operator expression or another function application expression. Here we have a literal expression 4. So how does such an expression get evaluated? And this is where the lie comes in a little bit. First, you evaluate this variable name or identifier expression, and that gets evaluated to a function value, the actual function that does subtraction of natural numbers. Then you evaluate this expression, and this gets reduced to 11. Then you evaluate this literal expression, and that gets reduced to the number 4. Then you apply this function to those reduced argument values 11 and 4, and the subtraction function runs. It takes 11, it reduces that 4 times by 1, 11, 10, 9, 8, 7, and the result at the end of the day is 7. Okay. So here are some other natural number operators or functions in lean. As you'd expect, you can compute products in lean. So 6 times 5 is 30. You can compute quotients in lean. So if we take the quotient of 6 and 5, what is the quotient? 6 divided by 5. How many 5s are in a 6? Yeah, there's 1, right? Okay, so, whoops. I didn't put the operator in there. So 6 divided by 5 is 1. Be sure you understand integer division operations. And so the quotient 6 divided by 5, just like you learned in, what 4th grade or 5th grade, is 1. And the remainder function, also called mod, is represented as in many other languages with the percent sign. So 6 mod 1 is, 6 mod 5 is the remainder part of the answer. It's 1. Okay, so these two lines together, if you go back to your 4th or 5th grade class where you learned about division, you would say that 6 divided by 5 is 1 remainder 1. Okay, so good. Now I'm going to tell you how function application really works. It's just a little bit more complicated, but this is an idea that you probably haven't ever seen before because you haven't been using languages that are functional. So what is a functional language? Well, a functional language is a language that makes it really easy to deal with functions. Functions in a functional language are just values like any other value, and they can be passed around as arguments. They can be stored as the values of variables. They can be constructed and returned as the values from other functions. So functional languages treat functions as first-class citizens, just like natural numbers, strings, booleans, and anything else. Okay, so let's talk about this, how this is actually working here. So we've already seen, and I'm going to just cut and paste this down here and give you a new topic name, and I'm going to call this partial evaluation. Okay, I'm just going to cut and paste that back in there. So we've already seen that the function application expression 6 plus 5 immediately gets desugared. Okay, you get rid of the syntactic sugar of that infix operator and replace it with just a function application expression, which starts with the name of a function or a function valued expression applied to two argument expressions. Okay, and now what actually happens here is the following. First, you replace the name of the function with its value. Okay, and the way that you can see what the value of this identifier is, what function definition it's applied to, it reduces to, is using a command called print. And you're not going to like what you see here. Okay, so I'm going to say print nat.add, and over here you get the result. Okay, and this is some kind of advanced lean stuff. You're not expected to understand what all of this looks like. But here's what it's telling you. It's saying, well, nat.add is a function. Okay, it's a protected definition. We're not going to talk about protected. It's a definition. The name of the variable or identifier is nat.add. And what's its type? Well, the type of this function is a function that takes a natural number as an argument. and then it takes a second natural number as an argument, and then it reduces to or returns a result that is also a natural number. So we say that addition is a binary function, a binary operator, because it takes two arguments. But the type of add is nat to nat to nat, because it takes two natural number arguments and then returns a third natural number as a result. Okay, and you can see that this function, nat.add, of this type, nat to nat to nat, is defined to be nat.add._main. That's an implementation detail. That's just another function. Okay, so if we really wanted to see the implementation of nat.add, we need to look at the implementation of that thing. So we'll print that out, and here it is. Okay, and there's the definition of addition. Now, this looks very complicated, and it is. And I just want to point out, and it's not actually. Okay, it's complicated. It's much more complicated than it needs to be because lean is built in a very general way, and this is using kind of advanced lean. We're not going to have to deal with anything quite like this. The critical thing to see here is this special character lambda, and whenever you see a character lambda in a functional programming language, the first thing you think to yourself is, oh my God, it's Greek. Then the second thing you think is, oh, it just means a function. Okay? And so this entire expression right here is a literal expression that represents a function. And in particular, it's a recursive function that implements natural number addition. We're not going to delve down into how this function works right now, but we'll see how addition is implemented on natural numbers shortly, and it's beautiful and simple. I just want you to see that when you're evaluating an expression like this, the first thing that you do is you reduce the name of the function to its value, which is one of those lambda expressions. Then you reduce the first argument to a value. The lambda expression is an expression of a function that takes one argument and then returns something. So, how do we proceed from here? How do we make sense of what's going on? Well, if you're a little confused now, that's okay. I'm going to try to bring it together for you now. Let's look to see what is the type of nat.add. Can you tell me what you think the type of nat.add is? Oh, yeah, nat.add is just a function that takes one natural number and a second natural number and returns a natural number. Okay, so I'm going to copy this into my copy buffer, and I'm going to make a little comment here, and I'm going to remember that the type of nat.add is nat to nat to nat. Now what I'm going to tell you is that this arrow operator is what we call right associative. And what that means is that if you don't see any parentheses in an expression like this, it's because they're implicit. And where they go in is defined by the associativity of the operator. In this case, it's the arrow operator. So nat to nat to nat really means this. So the type of nat.add really is this. And what does this say? This says that the type of nat.add, it's a function that takes a natural number and returns a value of this type, which is another function. And it's a function that takes a natural number, the second argument, and returns a value of this type, just a nat. So now you're done. Believe it or not, this is how evaluation works. It's beautiful, and it's called partial evaluation. So let's start again with, let's just take this expression right here. Okay. We believe that well, let's check its type. Well, its type is going to be what? Its type is just going to be nat because this expression evaluates to a natural number. But what we just said here, we know that the type of nat.add is nat to nat to nat. We know that we now know that arrow is right associative. So that means implicitly parentheses are added from the right going left rather than from the left going right. This is correct. This is not. Nat \2 \nat 2 nat. If arrow were left associative, then this would be the meaning of nat to nat to nat, but it's not. If this were the type of nat to nat to nat, what would that mean? Well, that would mean that addition takes as a first argument a function and returns a natural number. That's not at all what we mean by addition. Rather, we mean that addition takes a natural number, then it takes another natural number, and then it returns a natural number. So there's no function arguments at all involved here. But we also know that arrow is right associative. So what this says is really what nat.add is a function that takes a natural number, its first argument, and then that returns a function that takes a second argument and returns a natural number. So now if we look at this expression here, we ought to be able to say, well, nat.add takes a natural number, a single natural number as an argument. We ought to be able to put in parentheses like this and have things work. And it does work. So what's happening here is that nat.add applied to 6, that's a function application expression. In Lean, you can think of nat.add as taking 2 arguments and returning a third one. That's a natural way to think about it. But what's really going on is that a function in a functional programming language like Lean or Haskell always takes 1 argument. Sometimes what it returns is just a plain old value, but sometimes it returns a function that then takes the second argument as its argument, and that finally returns the right result. Okay, so this is weird. We can see that it's working, but the question I'm going to try to answer now is, what's the meaning of this function application expression? What's its type, and what's its value? Well, what do you think its type is? What's the type of this application expression? What kind of thing does it return? If I apply nat.add to 1 argument of type nat, what kind of thing do I get back? I get back a function of that type, nat to nat. So let's see, let's take this out here, copy, and let's check the type of that term. And sure enough, look at that. Nat.add applied to 6 is this weird thing. It's a function that Lean represents as 6.add. It's like add with the first argument already fixed to be 6. So this is a specialized version of add that only takes 1 argument now, and that returns a result. So if I apply this function here to a number like 11, what's the answer going to be? 17. So this is the function that adds 6 to whatever argument you give it. So here's a term. It's an application of the addition function to its first argument, yielding a new function that adds that first argument to whatever argument this new function gets. So if this thing is a term in Lean, I ought to be able to bind it to a value to an identifier or a variable, let's do that. Let's define, let's call it add6 to be this value here. Okay. So what kind of thing is add6? What's its type? Yes, its type is nat to nat, and we can confirm that here by explicitly specifying that the type of add6 is a function that takes a natural number and returns a natural number. And the function add6 in particular is this function right here, the function obtained by applying nat.add to the value 6 to get a new function of type nat to nat that adds 6 to its argument, which would be the second argument to the addition function if you view it as taking 2 arguments. So add6 now ought to be, and is, a function, so we ought to be able to apply it to arguments. So what happens if we evaluate this function application set expression, eval, add6, and we want to apply that to, let's say, 5. Well, there's your 11. What if I apply it to 11? There's 17 because I'm adding 6 to 11. So look what we just did. We think of nat.add as a function that takes one argument and returns a function that takes a second argument, the second argument to the addition, and that returns a final result. Okay, so when we evaluate this expression here, let's actually sort of look at how all this works. The first thing that happens is, well, the first thing we need to do is we need to understand that that is really grouped like this. So is function application right associative or left associative? Aha. Arrow is right associative. Application is left associative. So the way to read a function application to multiple arguments is as a function application to one argument on the left, possibly returning a function that then consumes the next argument. So if I had a function that took 4 arguments, like foo, a, b, c, d, you go ahead and put in the parentheses in the right way. Okay. Function application is left associative. So let's go ahead and put in the parentheses in the right way here. This looks like a function that takes 4 arguments and returns some kind of result, but the way that it really works is it takes one argument, a, and returns a function that takes 3 arguments. So that function right there can then be applied to one more argument, which would be the b, resulting in a function that then expects 2 arguments. So then the application of that function is applied to c, which returns a function that takes 1 argument. Okay? And then the application of that function that takes 1 argument to 1 argument finally results in a value at the end of the day. So this is a process called currying, C-U-R-R-Y-I-N-G, a term named after Haskell Curry, one of the early inventors of mathematical logic, theory of computation, and functional programming languages. It's also called partial evaluation because we don't fully apply foo immediately to all of its arguments. We apply it to a part of the argument list, getting back a function that then consumes the next, that then consumes the next, and then consumes the next. So think of it as Pac-Man, if you will. Foo consumes A, resulting in a new function that consumes B, resulting in a new function that consumes C. Resulting in a new function that consumes D, and at the end of the day, the application of that function to D spits out a final result, and now there's no more functions to evaluate. And so this reduces to a value at the end of all of this. And this is really, really cool because we can use partial evaluation as kind of machinery to manufacture functions. So we could define add3 to be the function nat.add3. You see, I can apply nat.add not just to 2 arguments, but just to 1. So now this is a function that adds 3 to its 1 remaining argument. I can add, I've already defined add6. I can define add4 to be a function that adds 4 to its argument, and so on and so forth. Okay, and so that is really something that is pretty darn cool. So now let's take, as a kind of a final topic before a wrap up, let's just talk about, evaluation of expressions, which you can think of also as the interpretation of expressions, in the sense that we talked about at some length in the last lecture. Because what an interpretation does is it assigns to each symbolic expression a corresponding value. Okay? And now what programming languages do, or particularly functional programming languages like this, is they define a set of rules that can be followed by a computer for interpreting a given expression by evaluating it or reducing it to a value. And in that way, every expression in the language is interpreted as meaning a corresponding value in the domain of discourse. So here, the domain of discourse is the domain of actual abstract mathematical natural numbers. The syntactic domain of expressions is the domain of expressions in lean that we've been looking at right here. Nat.add3, for example, is an expression whose interpretation is a function in mathematics that takes 1 argument and returns a result. So add3 is a variable that reduces to a function. Okay, so the domain of discourse here is not just that of the natural numbers, it's really the domain of arithmetic, which includes natural number objects, but also functions that operate on those objects, operators, if you will, and more. Okay, so I'm trying to bring this back to the core content of the last lecture and to have you see that the rules of evaluation here establish an unambiguous mapping from every possible syntactically correct expression here in lean to a corresponding value in a domain of discourse. Here, the syntactic domain of symbols is the domain of expressions that I can write in lean using arithmetic operations and literal expressions. The domain of discourse to which we interpret those expressions is the domain of abstract arithmetic, okay, where the objects are natural numbers that we have only in our minds, really, and functions, which are abstract functions that can be applied to natural numbers. So let's build one slightly more complex expression in the syntactic or symbolic domain and see how the rules of expression, the rules of evaluation would apply to associate that expression, that syntactic thing, to a corresponding value. Suppose, well, let's see, up at the top of our file here, we defined n1 to be 6. So let's write an expression that involves maybe n1 and n2. So here's my expression. Actually, I'll just write it like this. We'll define, result to be, how about add 6 applied to n1? What is n1? n1 is 6. We're adding 6 to that. So I'm sorry, result is here is what? It's a function. Okay, but let's take that function, add 6. add 6 is a function that adds 6 to its result. I just haven't printed out what result is. So let's actually just use eval here. Sorry about that. That's a little confusing. Okay, we're going to evaluate this expression, add 6 to n1. And of course, add 6, we know, is a function that adds 6 to its argument. N1 is an identifier that's bound to the value 6. And so add 6 n1 will be 12. If we used n2 here, which is 5, we'd expect to get 11. And we do right down here. So let me close out this confusing all messages window, and there's our result right there. Okay, so how does this expression get evaluated? It's a function application expression with a function valued expression on the left and an argument expression on the right. Add 6 is what? Well, add 6 is bound to this term here. So the first thing we do is we evaluate the name or the identifier add 6. It evaluates to this expression here. We evaluate this expression and it returns that function that adds 6 to its result. Then we have to evaluate one argument, n2. Well, that's a variable name and it's bound to this literal expression 6. So to evaluate n2, we first evaluate it to the literal expression 6. Then we evaluate the literal expression 6 to get the value 6. Now we have an abstract function here that takes a natural number as an argument. We have the natural number 6 here as its argument. And then we apply that function to that argument, and ultimately it returns or reduces to the value 11. What we haven't talked about here is how we actually evaluate function application expressions like that. The short version is that we take that expression that represents the function with the lambdas in it. Wherever there's an argument expression in that function definition, we plug in the value of the argument. And then we just reduce that expression to an answer. And it turns out that that answer reduces to 11. Okay. So I think that's probably enough for this lecture. We've taken a few very, very, very simple examples of the kind that you probably ran on your very first day in CS 1110 or 1111 or 12 or 13 or whichever 1110 early CS programming course you took. Maybe you cranked up the Python REPL and typed in 6 plus 5 and got 11. Okay, we've unpacked a lot of what's going on here in the evaluation of those kinds of expressions. We've talked about 3 fundamental kinds of expressions: literal, identifier or variable expressions, and function application expressions. We've talked about types and values. We've talked about how function evaluation actually works in functional programming languages, which is this beautiful concept of partial evaluation, and the idea that functions are just values too, that can be assigned to variables, just like we did right here. We take this expression, reduce it, we get back a function, and assign that function as the value of this variable. As we'll see going forward, function values can be arguments to functions, and functions can return other functions as results in functional programming languages. Now try to do that in Java, C++, or Python, and the truth is actually you sort of can, but only because the latest versions of these languages include concepts from functional programming languages, in particular a concept called lambdas, which are simply functions as values. Okay, but these languages are not like Java, C++, extremely complicated languages, and they have lambdas really as kind of a glue-on, whereas functional programming languages are founded on these fundamental concepts of functions as just another kind of object, and that's how mathematicians think of functions. As you get more advanced in mathematics, you take entire courses in which you're no longer working with numbers as objects, you're working with spaces or collections or sets of functions as objects. And you can talk about things like whether one function is less than another, or how close 2 functions are together, or converging sequences of functions. Okay, so discrete mathematics and mathematics abstractly, more generally, have as a critical component this idea that functions are just objects like any other kinds of objects we talk about, and you see that in this lecture here. As a final thought, what I want to begin to communicate is the idea that, we've looked at the syntax of expressions, arithmetic expressions here in particular. We've seen that we can define a kind of a procedure or an algorithm for evaluating these kinds of expressions. What we haven't really talked about is, what's the syntax of these expressions? I mean, I've showed you examples of syntax, but how would you formalize the syntax? How would you specify the syntax of a language of arithmetic expressions? Well, that will be the topic of the next lecture, okay? And you might have already guessed that because we can build bigger expressions out of smaller ones, all the way down to literal and variable expressions at the leaves of the tree, that maybe we define the syntax of language as an inductive type whose values are expressions in the language we're defining.